on with the field effect transistor amplifiers and switching circuits. Section 9.2, the common drain amplifier. If you refer back to our text on page 448, common drain amplifier, I've marked the introductory paragraph there. The common drain amplifier is comparable to the common collector BJT amplifier. Recall that the common collector amplifier is called an emitter follower. Similarly, the common drain amplifier is called a source follower because the voltage at the source is approximately the same amplitude as the input voltage and is in phase with it. In other words, the source voltage follows the gate input voltage. Should sound very familiar, né? As it was mentioned here about the BJTs. Anyway, if we go and look at the circuit, JFET common drain amplifier. Remember, we said we have to know how to identify the configurations of amplifiers. So I go and have a look again. Where's the input applied? Where's the output? What's the remaining terminal? And the remaining terminal is, of course, the drain. Alright, so this makes it a common drain amplifier. Alright, let's have a look what they say about the common drain amplifier in the textbook. As I said, it should sound all familiar because they are basically the same as for the BJTs that we've discussed. Anyway, a common drain JFET amplifier is one in which the input signal is applied to the gate, as we've seen, and the output is taken from the source, making the drain common to both the AC and DC signal. Because it is common, there is no need for a drain resistor. Okay, the common drain amplifier is also called the source follower, as we've seen, and self-biasing is used in this particular circuit. Let's have a look at the voltage gain just below figure 918. I've marked that first sentence in case you've just didn't notice it by this time. As in all amplifiers, the voltage gain is V out over V in. Of course, the formulas for V out over V in is different, but the voltage gain is always the output voltage divided by the input voltage. Alright, in this case, V out is IDRS and V in is VGS plus IDRS, is shown in figure 919. At the bottom of the page there. Then substituting ID is equal to GM VGS into the expression gives that following result, as we can see there. A is equal to GM VGS RS divided by VGS plus GM VGS RS. The VGS terms cancels, so the final equation for voltage gain for the common drain amplifier is GMRS divided by 1 plus GMRS. Right, again there, notice that the gain is always slightly less than 1. Alright, you can see there because of the formula. If GMRS is much larger than 1, then a good approximation is that the voltage gain is equal to 1. Since the output voltage is at the source, it is in phase with the gate or the input voltage. All sounds very familiar if we think back on the BJTs, no? Alright, the input resistance on the next page. Because the input signal is applied to the gate, the input resistance is seen by the input signal. Source is extremely high, just as in the common source amplifier configuration that we've discussed previously. Alright, then the gate resistor RG in parallel with the input resistance, looking in at the gate, is the total input resistance. R in then RG in parallel with R in the gate, where R in at the gate is equal to VGS divided by IGSS. But let's have a look at this example. It also gives you some exercise in using the data sheet again. Example 9.9. Determine the voltage gain of the amplifier in figure 920 using the datasheet information in figure 921. Also determine the input resistance. You must read the questions carefully, especially in the tests and the exams. Use minimum datasheet values where available. VDD is negative because it is a P-channel device. Alright, then if we go and have a look at the solution on the next page. Since RL is much larger than RS, I can assume that the AC component R lowercase s is equivalent to RS, DC component. Then from the partial data sheet in figure 921 GM, which you also know is on the data sheet YFS, let's go and see, can you find that value on the data sheet? Go and have a look on the data sheet. Can you find the value for GM, which is actually called YFS? Can you see it there at the bottom of the page? And remember what they said? What value do they use there? 1000 microsiemens. So remember, it's the minimum value, not the maximum value that's given on the data sheet. That's why I said read the questions carefully before you answer them. Alright, then the other one, okay, then I can go and calculate the voltage gain by using the formula as we have discussed. Voltage gain then GMRS over 1 plus GMRS. I get the voltage gain of 0.909. You don't have to go and write 909 times 10 to the power minus 3. Remember, that is just for expressing our answers in the metric way. There's no unit or anything used here, so you can write 0.909. Alright, then from the data sheet, IGSS is 5 nanoampere. Maximum at VGS of 20 volts. Where is IGSS? Go and look at the data sheet. Can you find it there? There it is. IGSS. And what value did we find there? 5 nanoamperes maximum, because there's no other values. Can you see there's no minimums and there's no typicals? Even though they said use minimum values, there's only maximum values given. Alright? So don't get confused there. Anyway, we go back to the solution then. IGS is then 5 nanoamperes. At VGS is 20. Then R in the gate, as I've seen previously, is VGS over IGSS, 4000 mega ohms. Then R in is RG in parallel with R in at the gate, equivalent to 10 mega ohms. Why do they say equivalent to 10 mega ohms? Because I know if I have two resistors in parallel, one is much larger than the other one, the total resistance will be close to, it will always be a bit less of course, but it will be close to the value of the smallest resistor. Alright. Okay, that is then the common drain. This brings us to the end of this section. Again, read through the questions and apply everything here, and now you have to do basic problems 24 to 27 for this specific section.